coming back again to the Stirling numbers of the first kind, and their signless counterparts, we want to prove this formula for the generating function. That the generating function fixing n for the Stirling numbers of the first kind, Cnk, is exactly the rising factorial for x's. I'm going to give two proofs of this. The first proof is going to be maybe semi-combinatorial, because we're going to make use of the recurrence relation that we had last time, which was C of nk. To get a permutation of n with exactly k cycles, we could begin with a permutation of n minus 1 with exactly k cycles, and in n minus 1 ways we can add the letter n, or we can begin with a permutation of n minus 1 with k minus 1 cycles and create a new cycle with just the letter n. So that's our recurrence relation, and we need initial conditions. So the initial condition of there's one way to do nothing, that would be C0, 0, but all the other terms with 0. So 0, k equals 0 equals C of, n 0. And this is for k not equal to 0, and this is for n not equal to 0. Okay, so those are our initial conditions, and we're going to use this to prove this formula. So the standard trick here is just to denote the right-hand side as a function. We're going to call it f sub n, because it's clearly got a recursive structure, and we're going to make use of that. So these rising factorials can be written in the following way. So I'm defining fn in this case, and now I'm going to say, well, that's obviously the same thing as take that last term that you added and take the previous f. So this gives me a recurrence relation for the f. So the other thing I need to do is write the generating function, or write the expansion of fn and give it some notation. I don't want to assume that it's cn. So we'll say this is the sum from k equals 0 to n, because of course this is degree n, of some numbers b in k, x to the k. And all I need to do is show that the numbers b and k satisfy the same recurrence relation and the same initial conditions as above. Well, the initial conditions are pretty easy to do. Just based on this formula, we know that if we take 0, 0, we get the empty product, which is 1. And if we take b and k with n times k equals 0, not both 0, then we get 0. So it has the same initial conditions, so now we need to show it has the same recurrence relation, and we're going to use this recurrence relationship to do that. So I will write down, well, I guess I can just go from here. So using the recurrence relation, fn of x is equal to x plus n minus 1 times fn minus 1 of x, which is going to be the sum from k equals 0 to n minus 1 of b n minus 1 k x to the k. So that's just using that top recurrence relationship. I've just plugged this guy in here. And now what I'm going to do is split this up into two terms, one with the n minus 1 and one with the x. I'll take the n minus 1 one first. This is the sum, k equals 0 to n minus 1 of b n minus 1 k x to the k, plus x is going to get multiplied in, this is 0, n minus 1, b of n minus 1 k x to the k plus 1. So again, this is, I've sort of crossed my terms here and done it like that. Okay, now let's get our indices shifted on the right-hand side. So this is going to be, oh, might as well put the sum here. Sum 0 to n minus 1, n minus 1, b of n minus 1 k x to the k plus, and here I need to do a shifting, so this is going to be the sum from k equals 1 to n minus 1. Well, sorry, from k equals 1 to n of b of n minus 1 k minus 1 x to the k. So that's just manipulating my exponents. And now we can see that combining these terms and then just kicking out the last bits that we need, we're going to get, and comparing with what we had, so this is going to give us the b0, 0 plus the sum from k equals 1 to n of n minus 1 b of n minus 1 k plus b of n minus 1 k minus 1, and all of that times x to the k. And now comparing the coefficients, this is therefore the coefficient b in k. It's exactly this recurrence relationship up here. So that tells us that the b in k's must equal the c in k's, because if you have the same recurrence relationship with the same initial conditions, you must be the same.